So there are two types of supernova, it turns out. One we talked about is what happens when a massive star reaches a iron core, and that iron core can't can't fuse any further. And the life cycle of that star, I want to mention when it starts fusing heavier and heavier elements, those elements take less and less time to run out. You can tell in watching a massive star about to supernova that the time it takes for the iron core to form and then for the final collapse to occur is about a day, and for the other layers it's going to be on the order of a year. The time it takes for carbon to build up in the core will be something on the order of tens of thousands of years for a low mass star. And it's going to be a lot faster, and the heavier elements fuse quicker, and so the effects that you see take a lot less time, but it's noticeable. For the second sort, what's called the white dwarf supernova, you have the star and it's slowly growing in mass, it's slowly accreting material, and if it reaches the limit for the size of a white dwarf before any of that additional hydrogen can fuse, then the carbon will suddenly start to fuse. It'll suddenly reach a point where the gravity will win. It'll overcome the degeneracy pressure. It'll force contraction, and the contraction will cause the carbon to start fusing, and there's no outer layer to stop it. It fuses all at once, and so it explodes. Now, the thing about this is there are lots and lots and lots of different sizes of massive stars. So there's lots of different massive star supernovas. Every white dwarf supernova occurs the moment the star reaches that limit. They are all exactly the same. Right? So an old massive star, lots of different layers, and it can be any sort uh, of of size. Right? So this process is unique between stars. And here's another arrangement of supernovas where we've seen them in different galaxies. And here's remnants of the supernovas. All right. And they're all going to look a little different if they're massive star supernovas. They're all going to have different features to them. And man, these are some pretty pictures. All right. And a lot of what you're going to see is the remnant giving off X rays, giving off energetic light, and it's causing gas around it to ionize. And so you see the ionized gas. And so we scroll through a bunch of these. This one is an image of the remnants of the supernova that occurred in '87. All right, what it looks like over several uh, years. All right, and you can see the remnant of it there. You can see the ionized rings of gas around it. All right, and you can see those same rings a little bit later. And in here, this is what I'm meaning by the uniqueness of it is the brightness of it, how visible the supernova is a function of time, and it has a decay curve. It looks like this. It has this sudden brightening. All right, the supernova occurs, it brightens up, and the initial matter around the star gets very bright. And then as it decays and as everything spreads out, it decays downwards. So more nebulous. But this is the important bit I was talking about earlier is massive star supernovas are all unique to themselves. They all have a curve. It looks like this blue curve. But the blue curve can take kind of any sort of shape. Every white dwarf supernova has this red curve. They all have that one.